In our world, every object has a predicted lifespan. For certain objects, their lifespan might be quite short, but for others, it will be virtually infinite. An ordinary human life seems to fly by in the blink of an eye compared to the lifespan of these goods. However, what will objects like stars look like in their final years? Will the day come when we can see what it's like to be a fading star? Will the alleged black dwarf ever be visible to humans? Hello, and welcome to Z. Please don't forget to subscribe and hit the bell icon. In astronomy, stellar evolution describes the series of alterations a star goes through during its whole life. This process can take several million to tens of billions of years, depending on the object's initial mass. A star often forms from a cloud of low-pressure, icy interstellar gas. The cloud compresses as a result of gravitational instability, gradually taking on a spherical shape. The young star's temperature rises steadily as a result of gravitational field energy being converted into heat and radiation during the compression phase. This stage's lifespan is directly correlated with the star's initial mass. The phase could last up to several billion years for the smallest stars and approximately 100,000 years for the heaviest ones. For example, the mass of our Sun is rather modest, and it spent about 110 million years in this initial phase. In the following stage, the star undergoes thermonuclear fusion, and its compression stops when the core temperature reaches a high enough level. After that, a young star, also known as a protostar, transforms into a main sequence star because the processes occurring at its core are the only source of energy for the star. Since this stage makes up around 90% of a star's life cycle, this is when the age of the star is initially determined. For example, our Sun will continue to exist in the main sequence stage for about 11.5 billion years. A star's chemical makeup, which is 91% hydrogen, is still quite similar to the interstellar medium when it enters its main sequence stage. Meanwhile, inside the star, the process of hydrogen changing into helium is ongoing. Consequently, the core undergoes compression and rises in density, leading to a steady acceleration of chemical reactions. This causes the star's characteristics to shift noticeably. For instance, only 70% of our Sun's current luminosity comes from its main sequence stage luminosity. The luminosity will be 2.2 times greater than it is now by the time the stage ends. It should be noted that not every star reaches the main sequence. The terms cold and hot subdwarfs refer to the exceptions that modern science is aware of. Although they differ from main sequence stars, some objects are quite similar to them. Subdwarfs are hence less bright and less rich in heavy metals. For main sequence stars, the last phase is likewise mass-dependent. A star typically either supernovas to become a neutron star or a black hole, or it sheds its outer layer to become a white dwarf. A supernova is a phenomenon that occurs when a star suddenly becomes much brighter and releases a lot of energy in the process. The flare then gradually diminishes. Massive particles are released from the outer layer in tandem with this explosion. Usually, the remnants of the star's supernova core form a compact object, which could be a black hole or a neutron star. Products of thermonuclear synthesis are among the matter emitted during a supernova explosion. Chemically speaking, the universe is able to evolve because of these elements. A main sequence star will eventually become a white dwarf, a hot, small-sized, highly dense celestial entity if its mass falls short of 8 solar masses. When our Sun eventually goes through this phase, it will shrink to 1/100th of its current size. White dwarfs are only bright because of their high temperature. They do not produce any energy. The surfaces of the hottest white dwarfs may be as hot as 70,000 kelvins, yet because of their small size, they are not very bright. Their average density is over 1 million times higher than that of main sequence stars. These objects progressively cool down and take on a red color because they are mostly made of a plasma of nuclei and electrons and have no thermonuclear energy sources. At a distance of 8.6 light-years, Sirius B is the nearest known white dwarf to Earth. This object is thought to be among the most massive white dwarfs currently known, with a mass comparable to that of the Sun. Its dimensions are the same as Earth's, and its volume is a millionth of the Sun's. It is estimated that around 120 million years ago, Sirius B changed from being a main sequence star with a mass of 5 solar masses to a white dwarf. Currently, it is estimated that 3 to 10% of all stars in our galaxy are white dwarfs. Variations in estimates suggest that about 97% of today's stars will eventually cool down to become white dwarfs. These objects will inevitably cool off and fade over time. All of these celestial bodies will eventually turn into black dwarfs, meaning they will stop producing any visible light. This process takes billions of years. For this reason, none of these objects have been observed by scientists to date. It is believed that the cosmos is now too young to have created any black dwarfs. However, similar objects that have lost more than 4,000 kelvins in temperature have already been identified by experts. The white dwarfs WD0346 plus 246 and SDSS J110217 are these objects. Most stars resemble black dwarfs when they reach the end of their evolutionary journey. Their mass is nearly the same as a white dwarf's. White dwarfs created during the formation of the first generation of stars are thought to have a temperature of about 3,200 kelvins and to appear as rather dim objects, according to today's models indicating the cooling of these stars. These celestial bodies might be among the hidden mass components of the universe. A white dwarf may need a quadrillion years or more to cool down to a temperature of just 5 kelvins. Theoretically, the process of dark matter annihilation becomes critical to the existence of black dwarfs when they cool fully. Although this process hasn't been directly observed in the cosmos yet, it's believed that during annihilation, dark matter particles would transform into common photons and release light that may be seen with the telescope. Black dwarfs are thought to cool and fade to the point where their temperature reaches the universe's background temperature if this process isn't allowed for. Nonetheless, theoretically, black dwarfs might continue to emit energy for a significantly longer time due to the energy obtained via dark matter annihilation. It is believed that dark matter annihilation will continue in these objects for over a septillion years, or as long as the galaxy halo is intact. It is only when dark matter destruction slows to a stop that black dwarfs cool off completely. Since the majority of human existence occurs in the phase and life of our universe that will follow the one we are currently in, it is unlikely that humanity will ever be able to find objects of this kind. We are living in a stellar epoch, which is a time when star formation is still occurring very often. This period will continue until the galaxies run out of interstellar gas. Low-mass stars, such as our Sun, will then begin to fade. After that, there will be a protracted period of disintegration during which the majority of objects in the universe will be brown, black, and white dwarfs. Everything in the universe will decay into elementary or subatomic particles during the era of black holes, while the remaining black dwarfs will either be swallowed by black holes or will entirely disintegrate. The end of the universe's life is predicted to be a period of perpetual darkness, during which space will be devoid of all energy sources. The universe will eventually cool to a temperature of 0. Space will eventually get larger, and in the presence of the final, extremely rare black holes, our planet will inevitably end in roughly 1 Gugol years. All remnants of former human civilization will have vanished by then. However, the course of the universe's existence could be drastically changed if we have any control over how it evolves. As for me, you inspire me to tell you all about it when you watch the Cosmo channel because people are still very interested in what the future holds for humanity. This implies that we still have the opportunity to make our imprint in the boundless reaches of our cosmos, even after such an unfathomably vast period of time. Thank you for watching and see you next time.